Welcome to the PH1105 e-lecture. In this short video segment, we will talk about the perception of sound. First, let us understand how we actually hear sound using our ears. So let's say sound wave is generated by a source, for example, a tuning fork, a guitar, or a piano, and it will arrive at our ears. And our ears, of course, there is the fleshy portion. This is actually to help gather sound waves and focus it towards the auditory canal. So this is a hollow tube that leads from the outside of the ear, the outer ear, to the middle ear where the eardrum is. Now this little piece of tissue is a little bony and it will vibrate when sound waves is incident on it. And then it will set into motion the ear bones. So this thing here is called the incus, the hammer, and then this tiny little thing here is called the malleus, the anvil, and then of course this tiny, even smaller thing is called the stirrup, and it will actually excite sound waves in the inner ear, which is called the cochlea. Now, just a piece of interesting fact, this little inner ear here, this little piece of ear bone, middle ear bone, is actually related to gills of fishes in the evolutionary of animals on Earth. Now, you can see this interesting shape of the cochlea. It has a spiral, and actually what it does is that it channels weak sound waves down the spiral channel, and which becomes smaller and smaller, so therefore it focuses the sound wave, increases its intensity, and then finally it arrives inside inside of the ear. And of course the inner ear is lined with a lot of very thin hair called cilia, and when sound wave passes by, those cilia is set into oscillation, and it triggers electrical impulses in the nerves that are connected to these cilia. So that's how we hear sound. Of course, the rest of the sound processing is done in the brain, and we will not talk about the brain. So let's move on to talk about the kind of the qualities that we assign to sound that we can hear in nature. First of all, we associate with sound loudness. For example, how loud the sound is. So this has something to do with the pressure fluctuation. So the larger the pressure fluctuation, the more the harder it will shake the cilia in the inner ear, and of course then the stronger the electrical impulses being generated by the cilia, so our brain will perceive it to be a louder sound. So this is the sensation of loudness. There's also the sensation of pitch. Okay, now it turns out that the cilia in our inner ear, they are not all the same length. So some are shorter than others. So those that are shorter will respond to higher frequency sound, and those that are longer will respond to lower frequency sound. So depending on which of the cilia generate more electrical impulses, our brain then interprets that as different pitches in the sound, or different pitches of sound. Okay, but in addition, we actually also can distinguish between different sounds of the same pitch, but different qualities. So we call that tone, color, or timbre. So for example, a harmonic sound wave like so sounds very boring. But it is fortunately for us, most of our musical instruments do not actually produce sinusoidal sound waves like this. They produce much more interesting. So you will see that we will find that actually, first of all, the pitch is determined by the lowest frequency harmonic in the sound wave. This is what we have after we perform a Fourier decomposition to get the Fourier series. Now you will learn the Fourier series next semester in the mathematics course, and also again in your second year first semester, also in a mathematics course. And of course, then you will understand how this Fourier decomposition is done. But for now, just accept that we can do that, and then we will find that the sound waves can be decomposed into different frequencies, and frequently there is the largest component, which is the harmonic. so that it determines the pitch of the sound, and then the rest will determine the color of the sound, so the timbre of the sound. Okay, so these are frequently overtones of the fundamental harmonic. So there are integer multiples, so they can be 2 times, 3 times, 4 times, 5 times, and 6 times, and obviously it's very difficult to generate overtones, harmonics that are like 30 times the fundamental frequency, because then that would you will learn when you learn more of the mathematical treatment of sound waves that the higher the frequency, the higher the energy density. So given a fixed amount of energy, you normally just excite the lowest harmonics. Okay, so now back to sound intensity. So we have talked about the pitch and the tone color, the timbre. So now let's talk about the intensity of a sound wave. So if the sound wave is sinusoidal, then this is the intensity is simply proportional to the square of the amplitude, the square of the frequency, and the square of the pressure amplitude. So this is related to the so if we want to and of course the thing here is because it is a wave, there is oscillation in time and in space. So what we hear is if we can record at very high frequency, we will find that the intensity changes with time. So it also oscillates with time. But because our ear is our brain and our ear together is not very sensitive to such instantaneous fluctuations, we actually perform time average, and that time average is of the pressure and the velocity. And so this is if you recall what you learned in mechanics, the force times the velocity gives you the power. So here it is pressure instead of force, because all you have to do to get a force out of the pressure is to multiply it by area. So for a sinusoidal wave, we know that the velocity is just del y del t. So this is omega a sine kx minus omega t. Now the pressure, of course, we have learned that already. It is also proportional to minus b del y over del x. So we can differentiate that, and we find that this is b omega k a square sine square of kx minus omega t. And if we take the time average of this quantity over one period, and you will do more of that in the second semester course on electricity and magnetism, we will find that the intensity is just 1/2 b omega k a square, or you can write it in terms of if you can eliminate k by making use of the wave velocity, and then you get square root rho times b, and then omega square a square. Okay, so for a sinusoidal sound wave, it is just p max squared divided by 2 rho v, where v is the displacement velocity, not the wave velocity. Okay, so the next, and then how do we measure intensity? We can measure it on a linear scale, but that will be very misleading, because actually our ear does not respond linearly to sound. Our ear responds logarithmically to sound, which is why we have defined a new type of scale called the decibel scale to measure sound intensity, beta. So this is 10 dB times log I divided by some I naught. I naught is called the reference intensity and is taken to be 10 to the minus 12 watts per centimeter square. So here in this table from the textbook, you can see the sound intensity level coming from various sources and representative. So a military jet aircraft 30 meters away, the sound intensity is actually 140 decibel. So if you divide by 10, then this is actually 14. So this sound level is actually 10 to the 14 times more. The intensity, of course, is 10 square. You can see that 10 square is 10 to the 14 times more than the reference intensity. And then the threshold of pain. So that means when you hear the sound and it feels painful, is 120. That corresponds to an intensity of 1 watt per meter square. And if someone is trying to drive a rivet into a metal sheet, then that sound intensity is 95 decibel, and you can see the corresponding intensity. For a train that is running on an elevated track, is about 90. Our MRT is actually more quieter than most trains, and then our busy street traffic is about 70 decibel. Okay, so it's already quite loud. An ordinary conversation is 65 decibel. A quiet automobile is 50 decibel. So this is what you hear when you're inside a car that is reasonably well maintained. And if you turn on your quiet radio at home, it's about 40 decibel. And if we whisper, then the decibel level is 20. And then leaves, which is barely audible, is about 10. And then there are some people who can hear the reference intensity at 1000 hertz, and therefore the sound level is 0. Of course, you need to have very good ears to be able to hear at this threshold of hearing. And of course, older people, the threshold of hearing tends to be higher because over time the inner ear loses cilia and therefore is less responsive to sound. Okay, so here's an example using decibel. If you move twice the distance away from the bird, so how many decibel does the intensity drop by? So if you move twice away, we know from the intensity formula, P1 over P2 is equals to the ratio of the distances. So it will be, so P2 over P1 is actually R1 square divided by R2 square. So we find that that is 1/4, and then the difference between decibel would be just 10 dB times log of 1/4, and that is -6 decibel. So this is -3, -6 decibels. This is pretty common. So every time the sound intensity drops by 1/2, you decrease by 3 decibel. Every time the sound intensity increase by 2 times, the sound in decibel units, it increases by 3 decibel. So thank you for listening to this video segment.